We shall begin 5th chapter of Physics class 11, Laws of Motion. Let us start with our common experiences. We know that to move a football from rest, somebody has to kick it. To throw a stone upward, one has to give it an upward push. A breeze causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without anyone rowing it. Clearly, some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop motion. In these examples, the external agency of forces like hands, wind, stream, etc. is in contact with the object, but this is not always necessary. A stone released from the top of the building accelerates downward due to the gravitational pull of the earth. Similarly, a bar magnet can attract an iron nail from distance. So this shows that external agency can exert force on a body even from a distance. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. The external agency may or may not be in contact with the body. So far, so good. But what if a body is moving uniformly? For example, a scatter moving straight with constant speed on a horizontal ice slab. Is an external force required to keep a body in uniform motion? The correct answer was given by Galileo in the 17th century, and that was the foundation of Newtonian mechanics, which signaled the birth of modern science. Now, from the practical life examples, Aristotle gave a law. The statement of his law is an external force is required to keep a body in motion. But now we know that it is not true. So we call this as Aristotle's fallacy. The Greek thinker Aristotle 384 BC to 322 BC held the view that if a body is moving, something external is required to keep it moving. So this is what he said, that if a body is moving, something external is required to keep it moving. For example, an arrow shot from a bow keeps flying as the air behind it keeps pushing it. So if you are shooting an arrow from a bow, it will fly in the air. Why? Because the air behind the arrow will keep on pushing it. Another example you can take is a boy playing with non-electric car on the floor. It keeps on moving till he pulls the string tied to the car. The moment he releases, it stops. So you have seen that if a boy is playing with a car and he has tied it with a string and he is pulling it. So as long as he pulls, the car will move. But the time he stops, the car will also stop. Therefore, external forces seem to be needed to keep bodies in motion. So these two examples plus many other examples in life, it says that it seems that to keep the body in motion, you require external force. Left to themselves, all bodies eventually come to rest. But if you leave the bodies to themselves, slowly they will come at rest. They will stop the motion. But actually it is not because of the absence of the external force. Why? Let us see that. A moving toy car comes to rest because the external force of friction on the car by the floor opposes the motion, its motion. What he says that now there is a friction force which is between the car and the floor, which will oppose the motion of the car, and that is the why the car comes at rest. To counter this force, child has to apply an external force on the car in the direction of motion. So if you want to continue the motion of the car, then the child has to apply the external force to counter the friction force in the direction of the motion of the car. If there were no friction, the child would not be required to apply any force to keep the toy car in uniform motion. If there were no friction, then the boy not required to give any force or he doesn't need to pull the car to continue the motion. It will continue. The opposing forces such as friction, that is for solids, and viscous, that is for liquids, forces are always present in the natural world, and these friction forces are present in the natural world. You can't avoid them. Therefore, forces by external agencies are necessary to overcome friction forces to keep bodies in uniform motion. So Why we apply the external force? Because to overcome the friction force which is present in the nature always. Okay, so that is why we apply the external force in order to keep the uniform motion, and that natural forces only to overcome the friction force. That is why what Aristotle said was wrong. That is why it is called Aristotle's fallacy, that he said that an external force is required to keep a body in motion, but it's not because of the to keep the body in motion we require, but we are going to overcome the friction force. That is why you require the external force. The law of inertia. Inertia means resistance to change. The statement of the law is a body does not change its state of rest or uniform motion unless an external force compels it to change that state. So inertia means resistance to change. Okay, that means if a body is at rest, it will continue to be at rest. If it is in motion, it will continue to be in motion unless an external force is applied on it. Okay, otherwise it tries to remain in its own motion. If it is at rest, then it will remain at rest. If it is in uniform motion, then it will continue the motion till external force is applied. Galileo studied motion of objects on an inclined plane. So he studied the motion on inclined plane. Okay, he did many experiments. We shall study the two experiments. Objects, number 1, moving down in inclined plane, accelerate, and number 2, moving up, retard. Number 3, motion in horizontal plane is an intermediate situation. So you can see in the first figure, in this figure, the object is on top, right, and it is coming down. So it is moving from top to down. So if the object is moving from up to down, moving downward, it will accelerate. Okay, here it will accelerate. And if the object is moving upward, okay, in this figure you can see it is moving upward, then it will retard. And if it is in the horizontal plane, it will neither have the retardation, neither acceleration, it will have a constant velocity. Okay, you can see in this figure. Moving on horizontal frictionless plane, object must neither have acceleration nor retardation, that is move with constant velocity. Okay, so this is the first situation. If it is coming downward, then it will accelerate. This is the second situation. If it is object is moving upward, it will retard. And if it is in the horizontal plane, but it should be frictionless, but that is not possible, right? But if it is frictionless, then it will continue to have a constant velocity. Okay, no retardation, no acceleration. Okay, so this was the first experiment. And the second one, a ball released from rest on a double inclined plane, the final height of the ball is nearly the same as the initial height, a little less but never greater. So secondly, he has taken double inclined plane. Okay, so this one is double inclined, you can look in this figure, right? In this he released a ball from the rest, from here, so it will come down and it will reach here. So what he saw, that he studied that, or he observed that it reached the almost the same height or less than the initial height. Okay, so that was the first case. If slope of second plane is decreased, the ball will reach the same height, but it will travel a longer distance. In the second case, what he did is that he decreased the height of the second plane. Okay, this one. So he decreased this. Then what he saw, that when he decreased this, the ball which is coming from here, it is moving, reaching at the same height, but it is traveling longer distance. If slope of second plane is 0, the ball travels an infinite distance, that is, its motion never ceases. In the third case, what he did is the slope of the second plane is 0. So you can see this is horizontal, right? So when he did here, it started moving and it will continues to move if there is no friction. Since there is a friction, it will obviously stop. So he said that it will go infinitely, the motion will never stop. So this is what he studied. There are many experiments, we have only 2 in our textbook. Therefore, Galileo arrived at a new insight on motion. The state of rest and of uniform linear motion are equivalent. So what he concluded, that the state of rest or uniform motion are same. In both, there is no net force acting on a body. So there is no net force acting on the body in the both. Okay, whether the body is at rest or in uniform motion. To maintain a body in uniform motion, we need to apply an external force to encounter the frictional force so that the two forces sum up to zero net external force. Now we have to apply the force. Why? If you want to continue, maintain the motion of the body. Okay. So if you want to continue the motion of the body, then you have to apply the external force. Why? Because you have to encounter the friction force. Okay. That is the reason. To encounter or overcome this frictional force, you have to give the external force so that the total sum will be zero. So net external force will be zero. Now we can state the Newton's first law of motion. The statement is, if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is net external force on the body. So if the force is zero, then acceleration is zero. If acceleration is not zero, that means there is some net force. Okay, mathematically you can say that if f equal to 0, that means velocity is constant and acceleration is 0. Okay, so that is what mathematically we can say. Now let us take example. A spaceship out in interstellar space, far from all other objects and all its rockets turned off, has no net external force acting on it, therefore A is 0. Okay, so suppose you have got a spaceship which is out inside in the interstellar space and it is far from all the other objects and all the rockets inside it are turned off, then there is no external force. That means acceleration is 0. If it is in motion, it will continue to move with uniform velocity. So it will continue to move with uniform velocity if it is in the motion. Now let us take another example. Consider a book at rest on a horizontal surface. So consider a textbook or a book on a table. It is subjected to two external forces. Now you can see that textbook is at rest. Then what are the forces on it? But there are two external forces. Which are the one? One is due to gravity, is weight W acting downward. So one is because of the gravity, due to its weight. Okay, it has got a weight. So due to gravity, there is a force on that. Okay, its weight W acting downward. And the upward force on the book by the table, the normal force R. And because of the table, there is upward force, that is a normal force R. Therefore, since the book is observed to be at rest, now you can see the book is at rest, right? Therefore, the net external force on it must be 0 according to the first law. So, according to first law, since it is in the book is at rest, that means the net force should be 0, right? This implies that the normal force R must be equal and opposite to the weight W. That means you can say that the normal force R and the weight W will be equal. Now we can see the motion, but we cannot see the forces. Okay, so we observe the forces, we observe the motion and we say that external force is 0, net external force is 0. That means R and W are equal. Now something more about inertia I want to say is, inertia of the particle is the measure of its mass. Larger the mass, larger the inertia. Now inertia, we already saw that it is a resistance to change, right? Now think of an example that you have got a bicycle and a truck is there. Both are in a stationary motion. So they have got the resistance to change. So they are at rest, they will continue to be raised. Now suppose you are going to push the push the bicycle, then it will be easily you can push because the weight of that mass of the bicycle is less. Okay, and suppose you want to push the truck, you will find it very difficult. Why? Because it has got the mass. So we can say that inertia of the particle is the measure of its mass. One more example of inertia you can think of, that if you are traveling or you are standing in a stationary bus and the driver starts the bus suddenly, then what happens is we get thrown down backward with a jerk. Why? Because you see that your feet are on the surface of the floor of the bus. Then you are standing, right? So what happens that your body wants to remain standing. You don't want to, as the law of inertia says that if you are stationary, you want to be stationary, you don't want to move. But now the bus is moving, there is a friction, so you also will move, and your feet will move and slowly your body will move. Therefore you get a jerk. If the sudden brake is given, then your body is in motion, so you will be forwarded. Okay, your body will forward. Why? Because your body wants to be in motion, right? But since bus has stopped, you also will stop, but you will get a jerk once again. Okay, that happens because the friction plus the inertia. Okay, So remember this, and we'll keep this much for today. We have studied the Aristotle fallacy, we have studied law of inertia and the Newton's first law of motion. Okay, thank you very much.